In this video, I would like to show you how to solve this problem by using 3D modeling in ABAQUS. So, we are trying to solve the same problem with the same boundary condition, with the same loads, and with the same profile. Okay, to help us in drawing this profile, it's better to know its coordinates. Okay, so that by knowing this coordinate of all these corner, so it's make easier when we like to draw this profile in ABAQUS. Actually, there are many ways to draw this profile in ABAQUS, like in SolidWorks, where we have many methods to draw one or certain parts. Okay, so for me, I would prefer to use this kind of method, for example, to know the coordinates. Okay, so by knowing the coordinates, so I can connect the point easily. Right, so let's have a look in ABAQUS. So in ABAQUS, the first thing that we have to do is to create the parts. As we like to solve the problem in 3D, so we have to choose 3D, and the type is deformable, the shape is solid, and the type of using the extrusion, and just click continue. So now we would like to create the lines. Okay, so I click this one. So either you can put the coordinate on this box. For example, the first point is -30 and 50. Okay, so ABAQUS will automatically acknowledge that point. And then the second point is 30 and 50. So ABAQUS will automatically connected these 2 points to create the line. Okay, instead of putting the value in this box, we also can directly create the line by referring to these coordinates. Okay, this coordinate is based on the reference is at this point, which is 0, 0. Okay, so that we have to draw the I-beam, okay, according to this reference 0, 0. So everything we need to make it like a mirror or symmetry. Okay, so the next point, I know that you will the thickness of the flange is 10, so I should go down by 10 in this case, so 30 and 40, and the thickness of the web is 5, so I will try to go to 2.5 here. Okay, and then the next point, this length in the middle part, if you look on this one, is 80. Okay, so half of it is 40, then the other half must be -40. Right, so the total here is 40, and then should go another 40. So the total length here is 80, and then here I should need to go back to the 30 and -40, and then the flange, the bottom flange is also the thickness is 10, so it should go down by 10. And here you can refer to this point. Okay, should be the same point. Okay, -50 and 30 and 50, and go up by 10, -30 and -40, and then here should be 25 as well. Okay, so that the thickness of this web will be 5. Okay, go up at this point 2.5 and 40. Next is to go to this point, and the last one this point. So it's done. This drawing has closed. Okay, has a closed profile. Next we can double check our dimension. Okay, this one should be 60, is okay. This one should be 80, also okay. This one also 60, is okay. The thickness of the flange is 10, is okay. The top flange also 10, is okay. The thickness of the web should be 5, looks okay. So everything looks okay. Next, just need to click the roller on your mouse. Okay, and then click done. And the depth, okay, as our length of the beam is 1 meter, which is equivalent to 1000 millimeter. Okay, in this case I still using the millimeters as my reference. So I have the beam. okay, our beam. Next is to create the property or the material properties. Okay, we are still using the same property, which is steel. Okay, using the basics property, which is the elastic property, is 200 E power 3, which is Newton per millimeter square. The Poisson ratio is 0.3. Then okay. Next is to create the section. Okay, so our section now is let's say beam 3D. Okay, so the category is solid, the type is homogeneous. Then continue. Okay, material used is steel, the one that we created just now. And here no need to click, just click OK. Alright, and then we like to assign that section to our part. So we just click this one, assign section, and then read this instruction. Okay, what you have to do. So next is to click the region that we would like to assign. So our part here, click done, and then choose section beam 3D, which is the material is steel. Okay, so now our part has turned into green color, meaning that this part is has the property. Okay, already has the property. So next is to go to assembly. Okay, to call the part that we like to analyze, which is our I-beam. Okay, this one, and make it independent, and click OK. Next is to go for step analysis. We are still using the same analysis, which is static analysis. So click static, then continue. Here I just follow with the default setting by ABAQUS, so I just need to click OK. Next step is to go to apply the loads and boundary condition, which is load. So let's try to impose the boundary condition first. As our beam, okay, on the left side is fixed to the wall, so just click this one, boundary conditions, choose symmetry, and then continue. Okay, instead of choosing this point, I'm choosing this surface, right? The whole surface at the back here. Then click done, and then I choose the last one. Okay, which all the deformation and all the rotations in all direction is 0. So click OK. Next is to impose the line load here in our 3D model. Okay, this load is based on line, but now we're not having line, but we have a surface here. Okay, a top surface here. So we have to convert the line load into pressure to take into account this surface. So we have to calculate the equivalent pressure, right? So to do that, okay, go back here. Okay, so first thing we have to get the resultant from the line load, which is 100,000 Newton acting in the middle. And then as we are having a surface here, okay, of the flange, the width is 60 millimeter, and the length of the beam is 1000 millimeter, so that this area, the top surface area, is 60,000 millimeter square. So pressure is force divided by A, so 100,000 divided by 60,000 is equal to 1.667 Newton millimeter square, or 1.667 megapascal. So we're going to impose this load in ABAQUS. So go back to ABAQUS. So create load. Okay. So in this case, we choose pressure. Continue and select the surface that you would like to impose the pressure, which is the top pressure. This one. Click OK and put the value, which is 1.667, and click OK. Okay, alright. So but our pressure is moving downward. So supposedly it should go upwards. We just need to change the direction by add the negative signs. And click OK and double check. Okay, now the pressure is moving upward, like in our problem. Next step is to go to create the nodes and element, which is mesh. So first thing, create the seed part, or we call it create the nodes. Okay, so I'm just follow with the recommendation from ABAQUS, which is the size is 50, because in this student version we have the limitation of number of nodes, which is up to 1000 nodes. So if you put the size is quite small, I'm scared that we will exceed the limit 1000 nodes. So to be safe, we just follow the recommendation by ABAQUS, which is 50. So I just click OK, done, and then click this one to create the elements. Click and then just click yes, and now we have the elements in our I-beam. Next is to assign the element type. So click assign element type and choose our parts, and done. And then check here, we're using standard, linear, and the family is 3D stress. The rest I just follow with the default setting by ABAQUS. So click OK, and next is to create the job, okay, so that we can submit the calculation. Okay, so create job. So let's say we name it like beam (3D). Okay, so just continue. Okay, and then open the job manager and then choose our beam 3D and submit. Wait until the status change to completed. Okay, now it's completed, so we can click the result to observe our result. So we click this one as a deform shape, okay, and this is in terms of stress, but our interest is more on the displacement. So we can see the displacement in y direction, which is u2. Okay, so if you like to change the view, so you can choose here from this viewport. Okay, we can try one by one. Okay, so maybe it's not suitable, this one is not really suitable, so maybe this one should be okay. So now we can check that the maximum displacement shown in this legend is 25.42 millimeter.